Hi, and welcome to 8.2 Power. In this lesson, students will be able to describe and calculate power. How powerful are you? So, critical thinking. Who is more powerful? Why do you think so? We have SpongeBob on the left trying to lift up a couple marshmallows, and we have Larry the lobster on the right successfully lifting up some heavy weights. Who is more powerful? But why, right? So Larry is obviously, I think, we would say the most powerful. Why is he the most powerful? Well, he's doing more work. There's a larger force that he needs to exert. Maybe they go the same distance. Maybe they lift it the same distance. Larry's a little bit taller than SpongeBob, but let's just say they lift their respective weights the same distance, but Larry needs to exert a much greater force than SpongeBob to do so. So hopefully you could see that SpongeBob is doing less work because work is equal to FD, and Larry's doing more work because it's force times the same distance, right? But just looking at the work, that is only one piece of what we need to look at when we're looking at power. So the real question is who's more powerful, not who's doing more work. Let's say instead SpongeBob has the marshmallow situation, and Larry is also going to have the marshmallow situation. He's going to lift that up instead. In that case, they would need to exert the same amount of force. So it just takes a little bit of force over the same displacement. And Larry would have to exert the same amount of force because it's the same weight. Let's say they're using this, right, marshmallow dumbbell there. And let's say they move it the same distance. Well, if it's the same force and the same distance, the work is the same. But who can do that work in a shorter amount of time? SpongeBob is really struggling. He's going to go, oh man, come on, and then finally get the thing up, okay? But Larry can lift that marshmallow thing super fast. So Larry does the same work in a short amount of time. SpongeBob does that work in a longer period of time. And what we're going to say is uh, that Larry is more powerful because he can do the same amount of work in a shorter amount of time. So in this case, again, Larry is doing more work in the initial case, so he is more powerful, but also Larry can do the same amount of work as SpongeBob, but in a shorter amount of time, so he is more powerful. So this is the formal definition of power, and we use a capital P to represent power. It says power is the rate of work being done with respect to time. In other words, how rapidly that work is being done. That's what power is. Power can also be described as the rate of energy transfer. So let's say you're transferring the chemical energy in a battery to light and heat energy in a light bulb. How fast is that energy being transferred? That'll say how powerful that battery is. So the definition for power, the rate of work being done with respect to time, gives us this formula. It's just the work divided by the time. But what is work equal to? Do you remember from the previous lessons? W is equal to FD. So instead, you could say the power is equal to the force times the distance divided by time. Distance divided by time, or displacement divided by time. We've seen that before. What is d divided by t equal to? V, right? d over t is equal to v. So you could just write the power is equal to the force times the velocity. All right, so there's all these different formulas for the work, but really it just boils down to it's the rate of work being done with respect to time. Don't forget that. Now, what are the units of power? Come on, answer me. What are the units of power? What are they? They are watts. All right, so a watt is a unit of power. You've probably heard of a 60-watt light bulb before. Okay, so watts are describing how powerful something is, and we use a capital W, all right, because watts starts with a W. Now that's a little confusing because we already saw, wait, I thought W was work. Yes, W is work. We use W to represent the physical quantity work. We use W to represent the units watts. So it gets a little confusing. Work is measured in what? Joules. Do a lot of work, you could buy a lot of joules. Power is measured in what? Watt is the unit of power. Okay, so don't get confused with the capital W. I know it'll trip you up eventually, and then you'll have a little bit of what they call a brain fart, but that's all right. How can you rewrite a watt? We said this before. This is a joule. Time is measured in seconds, so you could also write a joule per second. How many joules per second are you doing? How much work per second are you doing? That's how powerful you are. And we said a joule is just a Newton meter per second. And then look over here, we have a Newton and then a meter per second. So it's the same thing, Newton meter per second. Cool, so those are the units for power. What about horsepower? I thought the units for power was going to be horsepower. Well, it's not, because horsepower is a pretty dumb unit. A dumb unit that was developed by this really smart guy, James Watt, born January 30th, 1736, died on August 25th, 1819. He was a Scottish inventor, mechanical engineer, and chemist. The SI unit of power is named after him, the watt. He improved Thomas Newcomen's 1712 steam machine with his Watt steam engine in 1776. To help sell his steam engine, he developed the idea of horsepower as a way for consumers to make a comparison to their traditional horse-driven mechanisms. He was saying, "Oh, my steam engine is so powerful; it's like 12 horses. It has 12 horsepower." And he determined that a horse could turn a millstone, a mill wheel, 144 times in 1 hour, and estimated that a horse can exert 180 pounds of force. So you do the calculation out and you could determine how powerful a horse is. So he said that 1 horsepower is equal to 746 watts. Well, he didn't say that. He said in foot pounds per second is the units he had, because it's a force times the distance divided by time. That's power. But then he ended up getting the unit named after him. And if you do the conversion out, we could say 1 horsepower is equal to 746 watts. Wow, so that means that 1 horse is 746 watts. Wowzers, so that must mean that 6 horses has 4,476 watts. Just for fun, how many kilowatts is that? You might have heard of the term kilowatts. Do you remember how to change the base unit into the kilo prefix? It's actually 4.476 kilowatts. You just move the decimal point over 3 times. But wait, a horse has a maximum power output of around 15 horsepower, you might hear people on the internet saying, which is true. They can run at full speed, at full gallop, and they're producing 15 horsepower. Not just 1 horsepower for 1 horse, but 15 horsepower. Well, yeah, James Watt says, yes, but if you average the power output over the course of a workday, it's like closer to 1 horsepower per horse. So the jury's still out on how useful this unit is. It was really just kind of there to help people get used to the idea that steam engines are better than using horses. So we'll use the unit watt for power. Where is the formula for power? It is on the back page. Do you see it? Let's see. Oh, it's the very last thing. And get this, they give you that all the different forms. That's why I showed in the definition slide there. I gave you all of these forms of the power formula, even though it really just boils down to this. It's the rate of work being done with respect to time, which you can then extrapolate out because W is equal to FD, and we already talked about D divided by T is equal to the velocity. So that's nice that they give you all the different formulas there, but it ends up confusing people because it looks really weird. Hopefully you're not confused. It's just P is equal to W over T. Okay, so it's important to keep in mind that more power means work is done more rapidly, but it doesn't necessarily mean more work is being done. It depends on what the example is. So in this example, we have two elevators, one with a low power motor and one with a high power motor. So the low power motor kind of goes slower and the high power motor goes faster. It's the same amount of work being done though, because it's the same force. It's the weight of the elevator, the same weight on both sides. So it's the same force that you need to lift it up. And it's the same displacement. So W is equal to FD, same. So the amount of work is done is the same. Work is done in less time by the more powerful motor. All right, so you have that. If the time is less, that means the power is more. It's an inverse relationship. All right. Critical thinking, the graph below represents the relationship between the work done by a person and time. So this is a different one. All right. Previously in this unit, we saw an F versus D graph. This is completely different. This is a work versus time graph. Identify the physical quantity represented by the slope. Pause the video and try to figure out what the slope represents. Did you pause the video? Pause it. Come on, think about it. What does the slope represent? Well, the slope is just the rise over the run. And the y values are the work, and the x values are the time. Work divided by time. What does that equal to? Power. So here the slope is equal to the power. If it's a steeper slope, that means you're doing more work in a shorter amount of time and you're more powerful, and the slope corresponds with that, right? The value of the slope. If it's a shallow slope, you're not very powerful because you're not doing a lot of work in a long period of time, so you're not very powerful. That's how it works. So here's an example. It says a small electric motor is used to pull a crate with an applied force of 20 newtons at a constant speed across the floor. The crate is pulled a distance of 5 meters in 1 minute. What is the work being done by the motor? And what is the average power developed by the motor? If you want, you could pause the video and try this one out on your own. So I'm going to start by writing out the given information. The force applied is 20 newtons, and it's pulled a distance of 5 meters in a time of 1 minute. Now, if you left this in minutes, that's no good. You got to change it to seconds. So I'm just going to do it out the long way. I know you know how much 1 minute is equal to. It's equal to 60 seconds. But if you wanted to show that, boom, okay? What is the work being done? And then what is the power? All right, so part A, the work is equal to the force times the distance. So 20 newtons being exerted over 5 meters. So you're doing 100 joules of work. How fast are you doing that work? Right? What is the rate of work being done? What is the power? It's the work divided by the time. So the power is equal to 100 joules divided by 60 seconds. And you could say a joule per second for the unit. But instead we'll say it's 1.7 when you round it. What are the units of power? Watts. Okay, so here's the first instance where I'm like writing it out and it's a little confusing, like, oh, W for work, W for watts. That's a little weird, but that's what it is, right? So the work is measured in joules, the power is measured in watts. So don't get confused with the capital W there. And that's also a side note why in the beginning, way before, I like to use FG instead of some teachers, and it's fine, some people use W for the weight. Then you have W for the weight, W for the work, and W for the watts, and then this unit gets unnecessarily confusing. So I like to use FG just as a side note. It's really the definition of the weight is the force due to gravity. That's a big like side note over there. But yeah, that's how you do that one. All right, the world's strongest man can lift a 100-kilogram Atlas stone 1.5 meters into the air in just 2.3 seconds. How much power does he exert in lifting the stone? Just so you know, 100 kilograms is a lot. In the textbook, it says 70 kilograms is the average mass of a student in your textbook. That's what it says. So this is more massive than a person. They're lifting it up, and it's kind of awkward to hold that. It's a round stone, and they're lifting it 1.2 meters in the air and putting it in this thing. That's pretty crazy. That's pretty, he must be very powerful. World's strongest man, right? They're actually using, they use not experiments, but different trials that really prove, okay, you can exert a force over a distance the shortest amount of time. That's what makes you the most powerful. So it's an interesting thing they have on ESPN 8, the Ocho. That's not a real channel, but anyway. So we'll write the given information out. I see a mass and we're lifting something up, so I'm going to assume that the gravity is going to come into play. I want to make sure I get points for gravity here. All right, it says how much power does he exert in lifting the stone? Express your answer in watts and kilowatts. So we're looking for the power developed. Okay. We could go straight to, listen, if we want, we could do, okay, power is equal to work over time. We don't know what the work is. We could find it separately if we wanted to, but we also know that it's just equal to FD over T. This is in our reference table, so I will use that formula. The thing that's weird is this one. So you have the weight of the stone, and they're exerting an upward force on that stone. Let's say that upward force is exactly equal to the weight. Let's say they're balancing each other out, and he's moving the stone with a constant velocity upward. It's a constant velocity. It's not accelerating. That means these forces are balanced. That means the applied force, which is really this in our formula, is equal to Fg. So that's going to go over here, and we know Fg is equal to mg. So that allows me to do this. If you wanted to, you could also make this an H because technically we're lifting it up a height. And MGH is going to come up when we do potential energy, gravitational potential energy. That's a little side note. What was I going to say? If you wanted to, you could do the net force thing. In the y direction is equal to the applied force minus the weight. And if we're moving at a constant velocity, the net force is 0. This is the applied force minus, we could say mg. Now I'm just proving that's why it's mg. Then you add mg to both sides, and the applied force is equal to mg, and that's what we did. This is the applied force, and we're plugging in mg for the applied force because he needs to exert that force in order to overcome the weight. All right, so that's where this weird looking formula comes from. And then you could say the power is equal to 100 kilograms times 9.8 times a distance of 1.5 meters in the air divided by 2.3 seconds. And you get a power of 639 watts. So they're exerting, I was going to say exerting and developing. Both are good ways to say that. They're exerting 639 watts of power as they lift that stone. Cool. That's about it. Thanks for watching and have a great day.